Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a really interesting idea. Understanding is compression.
Yeah, I saw that title and I immediately thought of Solomon induction and minimum description length. It's a concept that's been kicking around for a while, but I feel like recent advances in AI are really bringing it to the forefront again.
I agree it's resurfacing, but I also think it's important to remember that compression isn't necessarily understanding. You can have a highly compressed representation of something that's completely meaningless.
Exactly. A hash function is compression, right? But it's not understanding. It's a one-way street. So what kind of compression are we talking about here? What makes it understanding?
Okay, so let's unpack that. The basic idea is that the better you understand something, the more efficiently you can represent it. Think about it. If you truly grasp a concept, you can strip away the irrelevant details and get to the core essence. That's compression in a sense.
Right. And that's where the link to things like Kolmogorov complexity comes in. The shortest possible program to describe something is its essence. It's the ultimate compression.
But how do you find that shortest program? That's the million-dollar question, isn't it? We can't compute Kolmogorov complexity in general.
And even if we could, I'm not sure it would necessarily equate to understanding. A really clever compression algorithm might exploit patterns that are accidental or coincidental, rather than reflecting any real underlying structure.
That's true, but I think the key is that good compression algorithms, the ones that lead to understanding, are the ones that capture the underlying generative model. They're not just about finding statistical regularities, they're about learning the rules that govern the data.
Okay, give us an example of that. How does this work in practice?
Think about language models, right? A really good language model can compress text much better than a simple dictionary-based compression algorithm. It's not just storing words, it's learning the grammatical rules, the semantic relationships, the common sense knowledge that underlies the text.
Yes, and those language models can then generate new text, which in a way is decompression, isn't it? Taking that compressed representation and expanding it back out into something meaningful.
That's an interesting way to look at it. But even the best language models still make mistakes, right? They can generate grammatically correct but nonsensical sentences. Does that mean they don't really understand language?
That's a great point. It gets to the heart of what we mean by understanding. Is it just about generating plausible outputs, or is it about something deeper?
I think it's about the ability to reason, to generalize, to adapt to new situations. A language model that can only regurgitate what it's seen in its training data doesn't really understand anything. But one that can use language to solve problems, to answer questions, to learn new things, that's a different story.
And that's where I think we need to go beyond purely data-driven approaches like deep learning. We need to incorporate symbolic reasoning, knowledge representation, the ability to manipulate abstract concepts. Compression alone isn't enough.
I agree. And I think spatiotemporal reasoning is crucial too. Understanding the relationships between objects in space and time, how they interact, how they change, that's a fundamental aspect of intelligence that's often overlooked.
So, if understanding is compression, and we want to build truly intelligent machines, we need to focus on building compression algorithms that capture the underlying structure of the world, including symbolic knowledge and spatiotemporal relationships.
Exactly. And that might mean moving beyond the current obsession with deep learning and exploring other approaches, like neuro-symbolic AI, or algorithms that are inspired by the brain's own compression mechanisms.
But isn't deep learning already doing that, in a way? I mean, the layers in a neural network are learning increasingly abstract features, which is a form of compression, right?
It's learning statistical correlations, yes, but it's not necessarily learning meaningful concepts. A neural network can learn to recognize a cat in a picture without understanding what a cat is, its properties, its behaviors.
And it certainly doesn't understand how a cat moves through space and time, how it interacts with its environment. It's just pattern recognition on steroids.
So how do we build algorithms that can do more than just pattern recognition? How do we build algorithms that can truly understand the world?
Well, one approach is to try to incorporate more prior knowledge into the model. Instead of just feeding it raw data, we can give it some basic understanding of the world structure, some axioms or constraints that it has to obey.
That's the idea behind neuro-symbolic AI, combining the pattern recognition abilities of neural networks with the reasoning abilities of symbolic systems.
And I think we need to think about how the brain itself does compression. How does it represent information in a way that's both efficient and meaningful?
That's a crucial point. The brain isn't just a big neural network. It's a complex system with multiple interacting components, each of which plays a specific role in information processing. We need to understand how those components work together to achieve intelligence.
We haven't even touched on hierarchical temporal memory and the work that Jeff Hawkins is doing.
Which is all about building models that can learn hierarchical representations of the world, representations that capture both the spatial and temporal relationships between objects.
Yeah, exactly. And that hierarchical structure is key to efficient compression. It allows you to represent complex information in a compact way.
So the takeaway is that understanding is compression, but it's not just about finding clever ways to compress data. It's about building algorithms that can learn the underlying structure of the world, including symbolic knowledge, spatiotemporal relationships, and the brain's own compression mechanisms.
And that's a much harder problem than just throwing more data at a deep neural network.
Definitely. It requires a more holistic approach, one that integrates insights from neuroscience, cognitive science, and computer science.
Absolutely. We need to stop thinking about AGI as a purely engineering problem and start thinking about it as a scientific problem, one that requires a deep understanding of intelligence itself.
Okay, let's drill down a bit more. Otto, you mentioned language models. Can you give us a more concrete example of how understanding is compression plays out in that domain?
Sure. Think about how GPT-3, for instance, generates text. It's trained on a massive dataset of text and code, and it learns to predict the next word in a sequence. In a way, it's compressing all of that information into its weights. The better it understands the patterns in the data, the better it can predict the next word, and the more efficiently it can compress the text.
But is it really understanding? I mean, GPT-3 can generate incredibly impressive text, but it doesn't seem to have any real understanding of the meaning of the words it's using.
It's like a really sophisticated parrot, right? It can mimic human language, but it doesn't actually understand what it's saying.
Okay, but consider this. If GPT-3 didn't understand something about the world, how could it generate such coherent and relevant text? It's clearly capturing some level of semantic information, even if it's not the same as human understanding.
Yeah, and think about how it can answer questions, translate languages, and even write different kinds of creative content. That requires more than just pattern recognition, right?
Yeah.
I still think it's mostly just very sophisticated pattern matching. It's learned to associate certain words and phrases with certain contexts, but it doesn't have any real understanding of the underlying concepts.
And it certainly doesn't have any common sense. It can make really silly mistakes, things that a human child would never do.
Okay, but that's where reinforcement learning comes in. You can train a language model to be more consistent and more accurate by rewarding it for good behavior and penalizing it for bad behavior. That's a way of injecting some common sense into the system.
But reinforcement learning can also be very brittle. If you train a model on a specific set of tasks, it might not generalize well to new tasks.
And it's still just pattern recognition at the end of the day. It's not actually learning the underlying principles.
So what's the alternative? How do we build language models that can truly understand language?
I think we need to incorporate symbolic reasoning. We need to give the model some explicit knowledge about the world, some rules and axioms that it can use to reason about language.
Like a knowledge graph or an ontology.
Exactly. Something that allows the model to represent concepts and relationships in a structured way.
And I think we need to think about how language relates to the real world. How do we ground language in our sensory experiences? How do we connect words to the objects and events that they refer to?
That's the symbol grounding problem, right? It's been a challenge for AI for decades.
So how do we solve it? How do we build language models that can truly understand language and connect it to the real world?
I think it's going to require a combination of approaches. We need to combine the pattern recognition abilities of neural networks with the reasoning abilities of symbolic systems. And we need to find a way to ground language in our sensory experiences.
It's a really hard problem, but I think we're making progress. We're starting to see some promising results from neuro-symbolic AI and from models that are trained on both text and images.
And I think we need to keep exploring new architectures and new algorithms. We shouldn't get too fixated on deep learning. There might be other approaches out there that are better suited for building truly intelligent machines.
Okay, let's switch gears a bit and talk about spatiotemporal reasoning. Donald, you mentioned that earlier. Can you elaborate on that?
Sure. So I think that Understanding the relationships between objects in space and time is a fundamental aspect of intelligence. It's how we navigate the world, how we predict what's going to happen next, how we plan our actions.
Like knowing that if you push a cup off a table, it's going to fall to the floor?
Exactly, and that requires understanding gravity, inertia, and all sorts of other physical principles.
It's not just about physics, though. It's also about understanding social interactions, knowing how people are likely to behave in certain situations and how their actions might affect us.
Right. Reading social cues, predicting someone's intentions, that's all spatiotemporal reasoning in a way.
Yeah, and current AI systems are really bad at that. They can play games like Go and chess at a superhuman level, but they can't even navigate a simple room without bumping into things.
Well, self-driving cars are getting better at it. They can navigate complex traffic situations, and they can even avoid pedestrians.
But they still make mistakes, and they don't really understand what they're doing. They're just following a set of pre-programmed rules.
And they rely heavily on GPS and other external sensors. They don't have a good internal model of the world.
So how do we build AI systems that can truly understand space and time?
I think we need to start by building systems that can represent space and time in a more structured way. We need to move beyond pixel-based representations and start thinking about objects and their relationships.
Like a scene graph or a world model?
Exactly, something that allows the system to reason about the spatial and temporal relationships between objects.
And I think we need to incorporate some common sense knowledge about physics and social interactions. We can't expect the system to learn everything from scratch.
So a combination of structured representations and prior knowledge?
Yeah, and I think we need to think about how the brain itself represents space and time. How does it create a coherent model of the world from all the noisy sensory information that it receives?
There's a lot of research on that, right? About how the hippocampus and other brain regions are involved in spatial navigation and memory.
And about how the brain uses different coordinate systems to represent space. Egocentric versus allocentric, for example.
Exactly. The ability to translate between different coordinate systems is crucial for understanding space. And I think that's something that current AI systems are really lacking.
So to bring it back to the original theme, building AI systems that truly understand space and time requires building compression algorithms that can capture the underlying structure of the world, including spatial and temporal relationships, common sense knowledge, and the brain's own representation mechanisms.
And that's a huge challenge, but it's also a really exciting one.
Definitely. It's one of the key challenges in AI research today.
Absolutely. And I think that if we can solve it, we'll be one step closer to building truly intelligent machines.
Okay, so if we were to give researchers some concrete directions for future work based on this conversation, what would they be?
From a deep learning perspective, I'd say focus on architectures that can learn more structured representations of the world. Things like graph neural networks and transformers seem promising, but we need to find ways to make them more efficient and more robust.
I'd say focus on neuro-symbolic AI. We need to find better ways to integrate symbolic reasoning and knowledge representation into neural networks. And we need to develop algorithms that can learn these symbolic representations from data.
I'd say focus on spatiotemporal reasoning. We need to build systems that can represent space and time in a more structured way, and that can reason about the relationships between objects in space and time. And we need to think about how the brain itself represents space and time.
And from my perspective, I'd emphasize the importance of biological constraints. We need to pay more attention to how the brain actually works, and we need to incorporate those insights into our AI algorithms. We can't just treat the brain as a black box.
Those are all great points. It's clear that building truly intelligent machines is going to require a multidisciplinary approach.
Absolutely. We need to combine insights from neuroscience, cognitive science, computer science, and other fields.
And we need to be willing to challenge our assumptions and explore new ideas.
Well, that's all the time we have for today. Thanks for joining us on Cognitive Spirals. We hope you found this discussion stimulating. Until next time.